Hey guys, today you are going to be learning your third formula to calculate a confidence interval for two proportions. So we have already looked at one proportion, and one proportion, for an example, is like saying a baseball player hits 20 out of 40 times. So that is a single proportion. I'm only going to give you one fraction. But for two proportions, you're going to get two proportions, or two fractions. So if I'm doing a two proportion interval confidence interval calculation, I might say in the problem that you pass or you complete 10 out of 30 assignments for math, and you complete 15 out of 40 assignments for science. So in this case, you're going to be getting two different proportions, and that's going to be how the formula differs from one proportion. Now, it doesn't necessarily matter which one you choose to be your first proportion and your second proportion, which that's going to make way more sense once I show you the formula. But it does matter how you interpret it. So we'll look at that later on. Okay, so this formula looks super scary, but it's really nothing more than just the single proportion, but now with two. So for a single proportion, you only had one proportion for your single value estimate, and you only had one of these guys under the square root for your margin of error. But now we've got two, and it gets a little complicated when you're calculating it, but I'll show you how I calculate it the best. But what I wanted to talk about is which one is your p hat of A, which one is p hat of B. So p hat of A is calculated by taking the number of successes for context A over the number of attempts for context A. And hopefully you're familiar with those words after watching the single proportion confidence interval calculation. And your p hat of B is context 2, or the second context, which is found by taking the number of successes for context 2 over the total of attempts. That 2 again comes from the 95% in the empirical rule. So a lot of people were getting on the quiz incorrect, is that if I wanted to calculate one confidence interval or a multiplier of 1 instead of a multiplier of 2, that means that I'd be going only one standard deviation away from the mean. So that multiplier would be 1. So that's just kind of like a go back to what we kind of talked about before spring break. So if I choose, going back to our math example, let's say that you complete 50% of your math assignments, so 50% of math, and we say that you complete 25% of science. So obviously you're completing more math than science. So if we calculate a confidence interval using math as our single proportion, as our first proportion or our first context, and I get an interval that's like 0.12 to 0.36, that interval is an entirely positive interval, suggesting that we would have evidence of you completing more assignments for math. However, if I said that p hat of A was science, which was less than math, and p hat of B, which is 0.5, which is bigger, then I might get a confidence interval that looks entirely negative. So like negative 0.41 to negative 0.07. And that would suggest that your proportion is higher for math, or your proportion is entirely lower for science. So this still would show evidence of completing more math. And that's because it's entirely negative, meaning when I subtracted, I found that in every case in my confidence interval that the proportion was higher for math, my second context, than it was for my first context, which is science. And again, what we're looking for as well is if we have a confidence interval that goes from like negative 4 to 0.31, that interval contains 0. So that means there's no difference in the proportions. So just some things to think about when you're calculating these confidence intervals. No difference in proportions. Okay, so the formula looks really ugly, but what is the single value estimate? What is the margin of error? So the single value estimate is the subtracted proportions. Okay, no matter what you choose, this p hat of A minus p hat of B is my single value estimate, which is my best guess at the true difference in proportions. It is not the true difference in proportions. This value can never be calculated. It's not the true difference, but it is my best guess at what I think it is. So you can never actually calculate a true anything, because that can only be calculated if you were given infinite amount of chances or an infinitely large population size. So this is my best guess. It's the single value estimate is not the true difference in proportion. And then this second half, this whole ugly bit, 2 times the square root of all this, that's your margin of error that we're going to be calculating. Okay, so we're going to need to calculate a p hat of A and n of A, and once you do that, you're going to be ready to just plug in the formula and hopefully find the confidence interval. Okay, so for our first example, from 2000 to 2009, kickers in the NFL made 377 out of 488 field goal attempts without a timeout being called. And they made 157 out of 197 field goal attempts after being something called iced, which basically means that if you're playing a football game and there's something that's really, really big on the line, and a kicker is about to kick a field goal, and that field goal could determine whether a team wins or not. Well, opposing coach might call timeout, and what that is hopefully doing is getting in the kicker's head, so he's freaking out and he's like, oh my God, so much pressure. And that's going to be what determines, we're going to see if there's actually a difference in the true proportion when this icing happens versus when it does not. So it's calculated 95% confidence interval for the true difference in the ability, which we're going to say true difference in the proportions, because we're not using ability as much anymore. So true difference in proportions to make a field goal. And if it doesn't explicitly tell us, like if you don't want to decide if it's p hat of A or p hat of B and you're getting kind of confused, a lot of the times you're going to see this parentheses, and that's going to help us determine what is p hat of A, what is p hat of B. Okay, so p hat of A is the proportion of iced completions. So it says he made 157 out of 197 when he was iced, and he made 377 out of 488 when he was not iced, so when they didn't call timeout. And the first thing that I always do when I start is I say, okay, let me calculate p hat of A. So how many successes did he have when he was being iced? He had 157. That's the amount of successes out of how many total, which is 197. And I'm going to calculate that proportion, and that's going to be what I'm plugging into my formula, so 797. Okay, so for p hat of B, that's going to be how many successes he had when he wasn't iced, which is 377 out of how many total attempts, so 488, and that gives me the proportion of 0.773. Okay, my n of A, that's the only other variable that I need for the formula. That's the number of attempts, so 197 for context A. N of B is 488 for context B. And I'm going to go ahead and write the formula again, even though it's really long, just so you see it one more time. So p hat of A minus p hat of B, again, that's my single value estimate, plus or minus 2 times the square root of p hat of A, 1 minus p hat of A, over n of A, plus p hat of B, 1 minus p hat of B, all over n of B. Okay, and now I have everything that I need to substitute into the values. So I'm just substituting and using a calculator, which sometimes can be the trickiest part. So 0.797 minus 0.773 plus or minus 2 times the square root of 0.797, 1 minus 0.797, all over 197, plus 0.773, 1 minus 0.773, that's coming from context B, all over 488. All right, so how in the heck are we going to plug this into the calculator? Well, what I do when I do this is I first find this value inside. And once I do that, I add it to this value. So I find everything underneath the square root first. And once I do that, then I take the square root. So find the inside first, and you don't really want to round too much because rounding is going to throw off your confidence interval. But if you're getting confused and you're not understanding where to put parentheses where, then just calculate this one at a time, round it, try to keep like 5 decimal places because that's going to help you when you're rounding. Okay, so I'm going to go ahead and subtract this. That gives me 0.024. Again, my single value estimate plus or minus 2. Everything including the square root is 0.034. Make sure that you check and you can get this value from your calculator. If you need help or you need a website that's going to help you with these calculations, then just make sure to message either myself or Coach Lowe and make sure that you know how to find the answers when you don't have a calculator necessarily. There's a lot of really good websites. So 0.024 plus or minus, multiply the 2 by the 0.034, which is going to give me 0.068. Okay, I'm going to take 0.024. Whoa, glitching a little bit here. Okay, so 0.024 minus 0.068 and 0.024 plus 0.068. That's going to give me my interval, negative 0.044 to 0.092. Okay, so that's the confidence interval for two proportions. So we're 95% confident that the interval of plausible values from negative 0.044 to 0.092 includes the true difference in proportion. So a lot of people on the quiz were putting parameter, but be specific what that parameter is based on the confidence interval that you calculate. So here is the true difference in proportion for kickers to make a field goal. Now I want to talk about real quick what it means that I have a negative to a positive. So since my interval goes from negative to positive, that means that my interval contains 0. So that suggests that there is evidence of no difference in the two proportions. So evidence of no difference between getting iced and getting not iced. So that 0 is very powerful in this example. Okay, for this example, we want to see if there's a difference between hitting against a right-handed pitcher versus a left-handed pitcher. So we have evidence, or we have data from Ryan Howard of the Philadelphia Phillies that he hit 126 hits out of 394 when facing right-handed pitchers and 46 out of 222 when facing left-handed pitchers. Notice this word only. He only hit that many out of left-handed pitchers. So this kind of tells me that this is going to be my proportion B. But again, it doesn't matter, it's how you interpret it at the end. So I'm going to choose right-handed pitchers to be P hat of A. So that's going to be right-handed pitchers. And P hat of B to be left-handed pitchers. So for right, I'm going to get 126 successes out of 394. And for my left-handed pitchers, he had 46 successes in 222. So that proportion A is 0.207. Proportion B is going to be, oh, excuse me, this is, okay. So proportion A, one more time, is 0.320, and proportion B is 0.207. Okay, and I already wrote the formula there for you. So N of A, again, is the number of attempts, the 394. N of B is the number of attempts for context B, which is 222. So I'm taking and just plugging in these values. I think the hardest part really is using the calculator, making sure that you're plugging everything in correctly. So make sure that you're practicing. I know that a lot of people may be struggling with this, so I suggest you practice. Over 394 plus 0.207, 1 minus 0.207 out of 222. That'll ultimately give me 0.113, my single value estimate, plus my margin of error of 0.072. So single value estimate, margin of error, my confidence interval is 0.041 to 0.185. So check to see if you were able to get that. So based on the confidence interval, do you have convincing evidence that he's better against right-handed pitchers? Well, in this case, my interval is entirely positive. That means you do have evidence. So I have evidence that he hits better against right-handed pitchers. All right.